Okay, so let's define certain operators. They're called ladder operators. So A plus is defined in this way, and the reason why we're doing this is because it provides a straightforward way of determining the spectrum of energy for the quantum harmonic oscillator. It makes other things fairly straightforward, and we'll come to that. But let's define this operator like that. Okay, so this looks like this is the momentum operator, and this is something that's proportional to the position. And let's define A minus, and the reason why they're called A plus and A minus, or ladder operators, is that when we apply this to an eigenfunction, it gives us an eigenfunction that is of higher energy, and this one gives us one that's of lower energy, and it will give us the spectrum. So we'll see that. But let's first define this and then build the Schrodinger equation in terms of these operators. So we again have momentum, but we have a minus sign here. So we're going to multiply these by each other to get a momentum squared, right? We want a p squared over 2m. We can see that when we take this and multiply it by this, these first two terms, we get a p squared over 2m, and that's like kinetic energy. And that's part of the Schrodinger equation. So here are the two operators. Now let's do A minus times A plus on some function, some wave function. Let's see what that looks like. So we have 1 over 2m times h bar over I d by dx minus I m omega naught x times this one plus I m omega naught x. Right, where omega naught is the frequency of the oscillator times psi. So let's work this through. This times this gives us minus h bar squared d by dx squared. So now we're doing, let's do this times this. We get a plus I m. So we have to be careful here because this times this means we have a plus h bar, right? We can get rid of the I. Then we have m and omega naught are constants, and d by dx of x. So it's d by dx of x times psi. So we really have to put the psi in here. So this is a d by dx of x times psi. Then we have this one. We have a minus m omega naught x, h bar, d by dx of psi. Here we have this times that, so we get a plus m squared omega naught squared x squared psi. Okay, so now let's work this out. 1 over 2m. Clearly this times this is the first term in the Schrodinger equation. The next term gives us, so we have the chain rule here. So we have m omega naught h bar. We take the first application involves the derivative of x with respect to x. That's just 1. So we have psi plus m omega naught h bar x times d psi by dx. We're going to get rid of this with this term. Right, this is equal to that. And then we have, okay, so we can, as we said, this term is equal to this. So these two cancel out, and so we get 1 over 2m times minus h bar squared, blah, blah, plus, let's add this term, m squared omega naught squared x squared psi, and that actually is the Schrodinger equation. That's the left-hand side of the Schrodinger equation, and so we have an extra little piece here. So we have an m omega naught h bar psi, and so this gives us minus h bar squared over 2m, two derivatives in the wave function in x, plus we have m omega naught squared x squared psi over 2, plus m h bar, the m cancels. I have h bar omega naught over 2 psi. And so the Schrodinger equation, of course, is minus h bar squared over 2m, two derivatives of psi in x, plus m omega naught x squared psi over 2 is equal to e psi, right? The time-independent Schrodinger equation looks like that. And so we have an extra term here that we want to get rid of. And so in terms of these operators that we defined here, we can say that here's one way of writing the Schrodinger equation. A minus A plus. We're going to have to get rid of this piece here, so we're going to do a minus h bar omega naught over 2 psi, right? So that would give us the left-hand side of the Schrodinger equation, and this would be equal to E psi. So that would be the time-independent Schrodinger equation, one version, one way of writing the time-independent Schrodinger equation in terms of ladder operators. So we can also now write this Schrodinger equation in terms of A plus times A minus, and we'll do that next.